Okay, so hello everyone. Let's get started. It's very few of you. We'll start from first talking about administration. So midterm is next week. And then what is the format for the midterm? Is task oriented. So you will have to solve specific tasks. And then the scope is from privacy 1 lecture until today. So we'll also cover today SSL attacks and defenses, as well as adversarial machine learning. And the timing for the midterm will be 45 minutes. So next week, we'll just do this midterm in this classroom. Any questions about the midterm? So, for example, we'll provide you, let's say, some tasks from privacy aspects. So, one of these tasks would be, for example, could be that you have to transfer from epsilon delta DP to RDP, or from RDP, for example, epsilon delta to epsilon delta. So we'll also provide, if necessary, additional, let's say, equations. You have to really like memorize everything what is there. So we will try to make it self-contained. Of course, it'd be good if you understand these topics deeply and you know where to find what and what are the important like equations or inequalities to use. But then it's more about just out of that how to solve a specific task.
Any code snippets, like based on the sign, or for example, you can give code snippet and ask us to do something.
So we will, I think, primarily focus on the content from the lectures. And then I think that for the code snippet, we won't ask questions about like programming, how to solve a specific task. It's more about like concepts that we cover during the lecture. Okay. So if no more questions about the midterm, so regarding assignment 2, so the second homework assignment that we planned. So the previous one was postponed by by at least 1 week. So we have to adjust the second assignment, and then we have to adjust its scope, so how difficult it is, and then also we'll adjust when it will be due. So based on your feedback from the previous assignment, we will try to make it so that it's for you understandable what should be done and how, and we will post that assignment at the latest next week. So we'll try to like make sure that you have all the information needed for the assignment. You have now also GPUs, so you can access the GPUs and then use them for this assignment. We will change the dates and adjust the assignment just for the information, and then we will release that at the latest next week. So, yeah, any questions about the assignment? Okay, good. So we'll just move on to the lecture about model stealing and defenses, but this time for SSL, which stands for self-supervised learning. Okay. Okay. So overall, most students ask very detailed questions. So thank you for that. I think that overall you did very well. So first we will start for the background. So I think that probably most of you haven't learned about SSL. So this is one of the, I think, challenges in this lecture. So we'll discuss more what are the main aspects for SSL, supervised learning. So the first question that was about SSL was, for example, can SimCLR be used in the NLP domain? So in general, if this contrastive learning can also be applied beyond image recognition, and if yes, how does augmentation work in these applications, for example, in NLP? So yes, the answer is that we use the same paradigm of supervised learning also in the NLP domain. And then we can, for example, collect many captions for a given image, and then we would like our, in this case, text encoder to give the same representation for these two captions of the same image. So one of these examples was with Flickr dataset. So then we had something like 5 captions by different users for the same image. And then this is forming positive pairs for this contrastive learning. So we give these sentences, for example, something like, how old are you? Is the same roughly semantically as what is your age? So these two sentences have the same semantic meaning. We pass them through this encoder, and we want this encoder to generate representations that are roughly the same for these two inputs that are semantically similar. And then standard also way how to train or pre-train these large language models is to also, for example, cover a given word and make the model predict what's the word. Can be also that we just want to generate next word, not only predict a given masked word, but we also want to just generate next word based on the context that was given to the model beforehand. And then regarding the augmentations, how we can augment these inputs. So there are some techniques how to do it. It's not as rich as in the vision domain. But for example, in the text domain, you can imagine that you might just cover a single word and then or change a word, for example, to its synonym. So these are ways how we can do some augmentations in the NLP domain. Any questions about this part? Okay. Now the question was in self-supervised learning, how to ensure that the model's generalization ability is there for new unseen data while avoiding overfitting to the training data. So simply in these cases, what is really done is the strong augmentations. So in supervised learning, augmentations are much weaker. So you have to just only, for example, in SSL, in a supervised models, just slightly perturb the image. Usually you, for example, like do horizontal flip and vertical flip. So very simple augmentations. SSL has much stronger augmentations. It also prevents the model from overfitting to the data. So usually this is one of the reasons why these models can be also applied to many different tasks. And then there's, I think, interesting question, and this was asked, I think, many times. Why there is this projection head necessary for SSL? Can the agreement maximized be maximized using model representations of both x sub I and x sub j? So only, okay, so the question was if this training of SSL can be done only on the level of representations. Here in this image is h sub I and h sub j. So can we just make sure that these two representations are similar for a given input? Why do we have to go to this z sub I or z sub I, this latent representations? And I think it's a very good question. And then why do we really do this projection head? So there are different ways how to explain that. One of them is that first, we can go beyond specific features of the input. So if we have very high representation, this h sub I, like high dimensional representation, we can contain many different details. If we want to, of course, for the generalization, we want them to be avoided. So then if we go to the smaller dimensional space, as in this z sub I or z sub I, then we can just abstract from these details and have a more general encoder. Another also way how people explain why do we use projection head is that ultimately for the training, okay, we have these representations, we have this latent z sub I, but then once we train this encoder, we want to use the encoder for downstream tasks. So then on top of this encoder, we also add, for example, classifiers or other layers. So to some extent, this projection head might imitate what's happening afterwards for the specific downstream task. Is it clear? Oh, this question, yes, go ahead.
So okay for you to speak up a bit because
Uh-huh.
kind of hard to hear.
Yeah, you can also come closer, please. Yeah. If anybody wants to come closer, please come. Okay. So any questions about the projection head? Is it understandable? I think it's something that was researched a lot. So to some extent, people actually were experimenting with different ways how to train the encoders, and they found that if we can add this projection head, then we can actually obtain better performance. So I would say in some cases it was just experimental finding that this actually head can improve the performance. Okay. And then for Dino, the question was, why do we use this cross entropy? So first of all, actually, yeah, we do use cross entropy, and cross entropy actually measures the average length of message between two different distributions. So this was also another way how we can measure this distribution differences. So ultimately, we want distribution from the teacher and student to be the same, and then it can be really done with cross entropy. So this is standard loss function. Yes. Yeah, so ultimately, cross entropy can be also used to minimize the differences between probability distributions. So if you have supervised learning, then your distribution is very simple. It's just 1 for the correct class and 0 for other classes. Here, it's a bit more complicated because you just don't have any specific label. So you have some distribution of these probabilities over the vector in Dino, and then you want these two probability distributions for teacher and the student models to be roughly the same. So you can just use cross entropy. You can also use other methods. You can just compare these two distributions and then just try to align them. So I think there is nothing more than just using that this way. I think there was also questions regarding why do we use exponential moving average. So I think that I did have a slide about that, I think. Okay, so here actually you can see something like this M, this exponential moving average. And the question was, why do we use this moving average? So this is a standard technique that is used also even for supervised learning. And the idea is that you don't update the parameters immediately after you see some gradient, but you have some averaging over checkpoints. And then this actually was shown to provide better performance. So you can imagine something like momentum. So probably some of you took this courses on deep learning, and then we saw that if you, for example, use the SGD with momentum, then you can preserve the correct direction in which you go. And the single example cannot really deviate you too much. This momentum actually can help. And the same is, intuitively, the same is for this moving average, that you just don't immediately copy the teacher, the parameters of the model, but you gradually update the teacher model. So this gradually updating the teacher model actually really helps. And then it's just also observed within the Dino framework that it can improve the performance. So again, to some extent, this was just observation from experiments, and they found that this approach really works better. Does it make sense? Okay. Okay, there was question in the SimSiam. It was told that only one of the view of the images is being sent through the projection head, but in the algorithm, why are both representations of Z sent through the projection head? So this is not the case. So here in this red rectangle, what we show actually is that we focus on one part of the loss. So the loss function here has two parts, okay? So in the loss, we have these values P1 and then Z2. So P1 indeed goes through the projection head and Z2 doesn't. So it just goes only through the encoder. So on the level of this part of the loss, you just pass one augmentation through encoder and predictor, other one through the encoder, and then you just swap it. So you just implementation wise, of course, like you want to be efficient, right? So you have these values computed and then you reuse them. So then you have the second part of the loss and you do reverse. So then you take P2 and Z1 after this red rectangle. But always for this computation of the specific loss value, you use one for projection and one from the encoder, the output values. Go ahead.
I think this was mentioned, but can you
Yeah.
repeat why we measured the similarity between the projected version and the set before the projection, like at the end, instead of just using it after both have been projected?
Why do we? You are asking why?
Why is the loss measured on P1 compared to Z2 instead of P1 compared to P2?
Yes. Okay. So what is really happening is that these encoders are the same. So you don't okay, if you just do it on, let's say, on P, then there's like just the same value. Yeah. Okay. Okay. So okay, I think that this is clear. Just I think that the pictures just shows one part of the loss, and then I gave the code to just give you more details. Okay, actually, this was the question about exponential moving average. So this was expressed actually also here. I just highlighted this red rectangle. So parameters of the teachers are updated using some, this is L value. So this is usually some large value like 0.9. And then we have small updates from the parameters of the teachers. So this is actually this moving average. So maybe what I can add here is that this is really something that is used quite widely in machine learning. Especially, for example, if you read something like paper about Adam optimizer, you learn that they also used something like Polyak-Roper averaging, which is just very similar concept. You have something like ensemble of models from the last checkpoint, and then you average these last checkpoints to get better performance. So this was just a technique used from other methods here in Dino to just improve performance further. Okay. So after that, we can move now to the main part about general model stealing questions. So the first question was why SSL is more vulnerable than supervised learning. So the simple answer is that just because SSL returns much more information than SL. So in the supervised learning, your outputs are just low-dimensional values, something like labels, or softmax output. So you, by default, you just release less information than in SSL, where you have high-dimensional representation. So simply by the fact that you have more information released, it's much easier to steal the SSL model. Okay. And the question was, why would you steal SSL encoder? So there are many reasons why. One of them is that you can have lower query cost. So it means that you don't have to query the API and always pay for your queries, but you can steal the encoder and then just locally do that without paying all the time these query fees. Can be also for the white box attack. So let's say that you have this API, you have to access all the time, but then how to attack the API, how to attack the model behind the API. You can first steal the model and then locally white box attack, and then transfer this found SSL examples to the victim model. So this is basically something like reconnaissance attack. You can also just, for example, earn money, meaning that there is this model exposed by API. You have to pay for the queries to the API. you can steal the model and then just expose it somewhere else to also earn money based on the stolen copy. Can be also that if there are two companies competing between each other. Let's say that you have something like one startup and second startup. They build these high quality models. Of course, they would like to outperform the competition. So they also might just want to check out what is the model behind the API for the other startup. Maybe you have some ideas how, why people would steal the models apart from that. Or any comments about this point? Okay. There was question, does the absence of labeled data in the training phase of the supervised learning result in being vulnerable to the extraction attacks? So there is really, in principle, no connection. So on the training side, we just can use or not the labels. But here in SSL, the main point is that the model does not return new labels, but we call it good features, right? So it's not that specifically you get some small information about the input, but something maybe even richer because it can be then applied to many different tasks. So in some sense, you can also think about representations as being labels, but not that you can directly use them. You have to just have additional middle layer or something like end layer, actually, like a classifier based on these representations. And there is a very, I think, good question regarding what is the difference between the stealing versus model distillation. So there are many differences, but I think that this was also a good observation that in some sense we can think about model stealing as being a form of distillation. And then what is the first difference is that in the model stealing, we have only black box access to the model, to the API. So we only access the model through querying the API and getting the answers. When we distill the model, actually we have our big model that we want to actually extract to a smaller model. So we have full access to the model. We can even take parameters of this big model to distill the smaller model. So we have full access and we can just try different ways how to distill the model. And then for the model stealing, we do access only the outputs, which can be softmax outputs, labels, or the representations, but usually nothing more. For distillation, you can have much richer information. For example, you can even use to some extent internal representations of the model that can be actually also useful for distillation. And then for a model stealing, usually you don't know exactly what data was used to train the victim model. So then you try to find something like a surrogate data set. Let's say that you have some model behind the API, you don't know what model was trained on. So you use, for example, data set like Lion 5B, which is a huge data set with many images. And you can just use that because you can just simply download that and then use for stealing. For distillation, usually you use the same data for training the victim model or the original model for distillation, and then use the same data to transfer the knowledge from the big model to the smaller model. And then for the stealing, usually you also do something like background work. So let's say that you want to prepare for stealing and you want to choose which queries you should ask the API to minimize the cost, to ask as few as possible queries. So this is like optimization behind the scenes to avoid being detected as an attacker of the model. For distillation, there are no such concerns. You can just do really distillation with all your data that you have. Then in model stealing, we minimize the cost. So we really want to minimize the cost of stealing to get the highest performance of the stolen copy, or also copy of the victim that is faithful, meaning that once you have the stolen copy, you can, for example, create this white box attack against the stolen copy. For the model distillation, what you usually optimize for is that you have this big model from which you distill the smaller model, and then you want to optimize the performance of the small model. You want this to be as performant as possible. And then usually for model stealing, you have the same architecture, or try to really estimate based maybe on some side channels, for example, like what's the representation output dimension. You want to use that information to infer what's the architecture behind the API. For distillation, usually the case is that it's a form of compression. So you want this model to which you distill to be smaller. For example, people distill from, let's say, models such as BERT large, so it's a model with 350 million parameters, to something like LSTM with like 1 million parameters. So you have much smaller model for distillation than what is really done for stealing. Any questions or any suggestions regarding this part? Okay. So let's move to the inference. So it actually is our way how to verify the ownership of a given model. So there was the question, the use of an arbitrator is explained as that it benefits the process of ownership resolution. So what really is done by the arbitrator? So how can we think about arbitrator is that it is a third trusted party. So let's say there's some court case, it can be just a court. And then the point is that we don't want to reveal this private data fully to the potential attacker. So why is this happening? Why do we have this constraint? Because if we reveal this data to the adversary, then they might just claim that they had such data and they just train model on this data. So this is one way how to avoid being accused of model stealing. So then if we have an arbitrator, actually this arbitrator receives both. Receives this data from the victim and also the so-called suspect model. And then on their own end of the arbitrator, they do the whole process of this inference, data inference. Okay. So the point is that the victim doesn't query the suspect model directly. Okay. And then there was question, does the metric for the mutual information score imply that the victim encoder and the stolen copy are both trained on the same data set? So no, it is not the case because, for example, your stolen copy can be trained on the stealing data, meaning that your model, for example, victim was trained on something like ImageNet, but you were stealing the model with Lion 5B. So different data sets, right? So the stealing is with different data than the victim's training. But ultimately, what we really measure through this score is how similar are representations from the victim and the stolen or suspect copy. And then we also observe that indeed, like with this score, we can find that if the stolen copy is trained with more of the stealing queries, meaning that you create more and more faithful copy of the victim, then the score increases. So it's just really based on the similarity of the output representations. I think it's also a very interesting question that for measuring the quality of stolen encoders, how do we measure the entropy mutual information? So here was the concern that we need probability distributions to calculate it, but how do we calculate these distributions? It's a very good question. So the answer here is that we compute this approximate score, and it is based on definition of mutual information. So this is still approximate, but tries to, of course, like, okay, this is approximate in the sense that it's not exact, and then we rely on approximations since we measure mutual information using also finite data. And then in practice, to compute such score, we can leverage this algorithm by Kozachenko-Leonenko, and they basically propose this algorithm to do that efficiently, and we leverage that also to compute our score. So this is actually a detail about in the background, like what you do for research to really solve some problems. So usually you have to really search through some literature to find the good ways how to solve such problems in practice. So I encourage you also to go to this link, for example, if you're interested, and check more. We have also actually other algorithms. For example, this is only for entropy, but also we have to compute this joint entropy, and we also have an algorithm for that, actually from the same people who invented these algorithms. Okay. So then the question was regarding these gas and mixture models. So of course, in practice, we use this multivariate case, and then we only compute the diagonal for the covariance matrix. So why do we do that? So because usually when we do the whole covariance matrix, these GMMs can overfit to specific data, and we don't want that. So we want them to be really more generic. And then it was, also we showed that experimentally, it was sufficient to just limit the covariance matrix to just be diagonal. And also actually thanks to that, we have quite fast computation of this covariance matrix. So there is no problem with getting these actually values. Okay. And then the question was, when attacker obfuscates representations, does this make the stolen model perform poorly? So short answer is no, because here the obfuscations are selected so that they do not harm downstream performance too much. So for example, we had this shuffling of the representations elements, adding some additional values, some transformations like affine, meaning that you just multiply every value by some constant, you add some constant. So we chose these augmentations or obfuscations because they do not harm performance of the downstream tasks. And we even actually checked that. So they're relatively simple. They are basically linear or affine. And then we checked that most of them do not really harm the performance. Some of them, if you do have something like binary representation, so you go from like these full values to like binary representation, and you just do some compression, of course you lose some performance. But in general, this kind of obfuscations are also designed so that we have different representations given to different users, but we do not incur any loss in performance. I think there's also something like question regarding why it is happening, what's the intuition behind that. So you can imagine that if you just shuffle the elements in the representation vector, then you still preserve the same features, right? They're just ordered differently. So then it's good for the single user who has the same order of representations, order of these features for each query. So then you can always use that. But for the attacker who receives these different outputs, then you might have to just map this. And the mapping actually is not that easy. Okay. So I think that I have to also comment more about what is the purpose of these Gaussian mixture models in our let's say inference. So first of all, GMMs, Gaussian mixture models, have nothing to do with enhancing the representations. So they are only used in this method to model property distribution of the representations. So GMMs are only for the model ownership resolution, for nothing else. And then they are easy to compute, and they are also fast to compute. And this is mostly because we just use diagonal for the covariance matrix. And then the main purpose is really to model a probability distribution of the representations from the encoders. And then finally, we just use the outputs from the GMMs, this log likelihood for the train versus test sets. So just this log likelihood, they just determine probability of having such representations in the train set or not. So this was purely for this purpose, and then had nothing to do with improving the encoder itself. Okay. And I think there's a very interesting question regarding the size of the private data. We also call it seed in the SSL encoders. So imagine that you can find the encoder using some public training data. So of course you can just scrape from the internet many data points. And then you might also include additionally into your training set this private seed, private data. And then the final verification of the ownership is done using private seed. So I think intuitively, if you have a bigger private seed, then you can, for example, use many more data points for verification. So your final statement about model being stolen or not is backed up by more data points. So in general, okay, like we also have to experiment that if you have this smaller private seed, smaller private data set, then performance of your final resolution of the ownership actually increases or decreases depending on the size. Okay, now we can go to the active. Okay, this question. Go ahead.
Yeah, it's still regarding the obfuscation, the representation,
Mhm.
and the test whether a model was stolen with the GNMs.
Okay.
Like, I don't understand how like shuffling the dimensions still preserves the distributions in a way that a GNM is actually useful to detect.
Yes, very.
In my mind, when I add a constant in some dimension or I multiply it, then I completely can change the distribution.
Very good. Very good. So what is okay? So I think that the core is that you compare train and the test set. So they both were transformed with the same obfuscations. So then ultimately what you really do here is that you do compare only train versus test, the same obfuscations. So then you compare against each other. So it's not like comparing, let's say, train with this shuffling and the test with different shuffling.
So you fit the GNM density estimator on the encoder that you suspect.
Yes.
Yeah, okay, so just an picture. Yeah, I see. Okay, then I get what.
I think it's a very good question. I think these are details that are maybe not visible directly. So, any more questions? Good. Okay. Okay. So now we can actually move to this active defense for SSL. We call it bugs for buckets. Okay. So the first question actually was, what if adversary queries the same way as the legitimate user? So here the answer is that adversary, by definition, wants to extract as much as possible from the victim model. So then from that perspective, in some way or the other, you have to differ from the legitimate user. And I think our main assumption here is that if you are adversary, you just want to extract more information from the victim model. So then this aspect can really make you stick out from the crowd of users. So this is the main, I think, intuition behind the active defenses. because in the active cases, you just as a defender, you have to really like find out if a given user who queries the API is an adversary, and you can do it just in this way by measuring information leakage. Okay. There was the question, if for embeddings trained on a model of length 1000, can we add 500 more random variables to make it to make the embedding length 1500, and can this prevent model stealing? So answer is no. Why? Because these obfuscations for bugs for buckets are only used against Sybil attacks. So it's just one part of the defense. It's not like you can use obfuscations to prevent everything. It's just used to make sure that different users get different kind of representations, and then they cannot easily map them to the same embedding space. So you have to have the whole machinery for B4B to really being able to really successfully prevent model stealing. So this is the whole machinery. So again, these obfuscations are really just one part, right, of the whole defense. So they are not, of course, it's not enough just to do obfuscations. And then the question actually here was, why don't we also utilize proof of work method in active defenses along with the bug for buckets? Okay, in this defense, right? So here in the bugs for buckets, we use adaptive noising, but nothing stops us from having other ways how we can change this component. So in general, the B4B defense was a framework. So it was not like this specific instance of the defense is the ultimate defense. No. So this was showing what are the steps really for SSL to prevent this model stealing. And then for each of these steps, so there are basically like 4 steps. For each of these steps, we provided one instance how we can realize, how we can implement this step. And then for this cost function, which we basically, like after we measure the information leakage and we map to some cost, this cost can be proof of work. In this case, we can easily just plug that in, or we can just present with adaptive noise. And here I think that because we have this high-dimensional space, so also having the noising is relatively easy to add to this defense. Okay. And then there was question, why didn't buckets reach higher than 60%, even with 50,000 queries? And the answer is actually easy, because we have many more buckets than the queries can cover. So here, the number of buckets actually is one of the parameters in the B4B. And there was one more follow-up question. How does the number of hash buckets affect the performance of B4B, which of course uses local sensitive hashing? So here we actually experimentally tested with different number of buckets. So we have, for example, here we covered from 2 to the power of 8 to the power of 14 buckets. What's happening is that if we have 2 to the power of 8, like this top left corner in this graph, then we observe that very easily we saturate the buckets, meaning that we get 100% bucket occupation. So definitely this indicates we have too many buckets. If we go to the other end of the spectrum, other extreme, for example, we have to the power of 14 buckets. So this actually is bottom right corner. So here the number of buckets occupied after 50,000 queries is only 20%. So this is just too small, because these gaps between the adversary who queries ImageNet and the normal users, they become too small. So if these gaps are too small, we're not able to differentiate between adversary and legitimate user. So you have to find a sweet spot, extract the balance, and then we just choose the parameters, like for example, the power of 12 or the power of 10, that can perform well and give us the separation of the users from adversaries, and also not to occupy the whole representation space, but after a small number of queries. Okay, so we can also now move to watermarking. The question was, will watermarking embeddings lead to poorer performance when these embeddings are used for other tasks? So in principle, what we really want to ensure is that we add the watermark in the SSL encoder, but we don't want to incur too much heat, too much of the decrease on the performance of the encoder itself. So usually watermark is relatively small, right? So the encoder is to express what are the best features for a given input and set high-dimensional features. And watermark is usually a very small part of the whole task for the encoder. Yeah, so yeah, this is actually blue circle was supposed to express that watermark is very, very small part of the input of the whole encoder. And then there's also a question, where do we do rotation, like how this really watermarking is performed. So actually, rotation is done in the input space. So before you pass the image through the encoder. And then there's also a question, how do you use the binary task for watermarking? So how do we go from these features, representations, to some binary answer? And here it is very simple. We just have the representations, but then we have some small model that just maps the representations to a binary answer. Is this rotation in a range 0 to 180 or in the range 180 to 360? So this is the way how we can easily go to this binary task for the watermarking.